Hello viewers, welcome back to the lab. This is going to be part 6 of the Quantel DPB restoration video series that I've been doing. There's been some progress made on what is going to be the hard disk emulator and floppy disk emulator as well, so we're going to look at that today. So before we get started, I just want to say thank you to my patrons who have been helping along the way. I can't do this without your support, and I noticed we have picked up a couple of new ones, so thank you very much. And if you want to become a patron yourself, there's links in the video description. I also want to thank PCBWay for their support. They are sponsoring this episode moreover than they normally do because they have actually produced PCBs for me. So those you will see later on in the video, but thank you so much, Elaine at PCBWay, for helping out. You're awesome. Right, let's get the camera turned around a little bit and I can show you what we've been working on. So before we get involved with the disk emulator, I just thought it'd be fun to go through some of the disk subsystem in the Quantel DPB, about how it works, because obviously I've been investigating a lot of this from my work with the GoTech on the floppy drive and also the emulator as well. So I thought it'd be fun to go through the 3 cards in the DPB which control all the disk accesses. So the main control part of this is the 2 cards here. This is the disk buffer card and this is the disk sequencer. These 2 are controlled by the computer cards, and these generate all the signals that go to and from the actual disk drives. That's the floppy drive and the hard disk. Now, just so we can get this card out of the way, this is the SMD interface card. These 2 cards here work at TTL level, so it's all 5-volt signalling. That's all fine, but the SMD interface is ECL. So this card is one that plugs in around the back of the machine, and this converts the signals that come out of these 2 cards from TTL into ECL. That's all it does. It's totally passive. So yeah, this just plugs in here, takes the signals from the card edge and outputs to the actual cables that go to the drives. So let's take a look at these 2 cards. We have the disk sequencer card. This one is actually the brain of the system. There is a very basic processor on here. It's the AM2901 and it's called a bit slice processor. Bit slice processors are an odd old school type of programming device. They're kind of used as like it's like half a CPU and half a state machine. It's a bit weird. Well worth going up and having a read on those though if you want to go and find a little bit more information. But basically the way this works is there is 7 programmable ROMs on here which hold microcode for the 2901 processor. What this card does is it receives instructions from the computer card to perform low-level disk tasks. That might be seek to cylinder, select head. So this does all the stuff that is involved with moving the heads around, checking to see whether it's on cylinder, whether the drive is ready, that kind of thing. So a lot of the SMD control bus is actually operated through the disk sequencer card. Now I should also mention that this card and all the code in these has been fully disassembled and taken to bits. That was done for the DPB emulator project by the Mog Miner. So there is going to be links in the video description if you want to go and see that code. So that is pretty much the disk sequencer card. It does all the stuff that is moving heads around and getting the drive into a position where it can actually transfer data to and from the drive. And the next card to look at is the disk buffer card. So this particular card takes the actual data that's coming in and out of the disk drives, brings it into here and processes it. This also handles the data clock. So when you're reading a drive, if it's the hard disk for example, the data comes in at 8 MHz as a serial stream, and that needs to be converted to 8-bit parallel to go actually into the buses that are in the actual DPB. When you're writing, this creates the actual clocks that go out to the drive. So if you're writing to the hard disk, then this would generate the 8 MHz clock to be sent out to the hard disk. This also contains around about 28 kilobytes of buffer RAM. You can see the SRAMs here static RAM, to act as a disk buffer. Now that is only for particular types of data. Not all of the data is actually sent into the buffer RAM. I'll explain a little bit of that a little bit later. One important aspect of this card is it has a sync byte detector. Now I have explained in previous videos the DPB disk format can be a bit odd, and the sync byte detector is part of that, and I will go into that in a little bit more detail later. This also has a 19,200 byte counter, and that is, again, because we've got such a bit of a weird format, it actually uses a counter. The maximum amount of user data that can be stored on a particular track is 19,200 bytes, and this counter acts as a backstop, if you like, the amount of data that goes to and from. This card can actually also steer where the data comes from and goes to. So if you're reading from the disk and you want to write to the brush store, for example, this card would steer the data from this card and send it onto the system bus, which would then go to the brush store. But if you actually wanted to read the data via the computer, it would load the data into the actual buffer RAM. So that is the disk buffer card. So I thought it'd be fun just to go into a little bit of detail about the Quantel DPB disk format. Now we've looked at the cards, we can kind of understand how they work, but what about the actual format that gets written to the disk? So first off, let's quickly go through what a standard floppy disk format might look like. The disk is divided up into tracks, and then each of those tracks is then subdivided into sectors. Now typically you would have maybe 40 to 80 tracks on the actual disk, and number of sectors would vary as well depending on what type of system you're using it on, but you know, it typically is between 8 and 20. Physically on the media there is also a small hole on the disk surface which provides a pulse out of the disk drive for every revolution, and that's usually used as a marker to say this is the start of the track. And in each sector of the actual disk on each track there's typically 512 bytes of user data. Now there is other data between the sectors, this is called metadata, and this identifies the actual sector number. It has some synchronization words in it as well, and it does have CRC and error detection information in there as well. So this provides for a reliable reading and writing experience. The computer can easily find tracks and sectors and just hunt out those bits of information. So that is what you'd normally find on a floppy disk. Now Quantel's disk format is rather different. Although the media is the same, it's physically the same, the biggest change is there is no sectors on a Quantel DPB disk. So again we have the circular media with the index hole. There's a slight reduction in the number of tracks for the actual drive that's in use on the Quantel DPB. It's up to a maximum of 67 tracks, which is just slightly less than what the actual hardware supports. As I just said, there is no sectors on a DPB disk. There is also no CRC and error detection information, so the data is just written straight on and there's no way to tell that it's come off properly or not. The data is MFM encoded, that's the same with all floppy disks. Now in terms of the actual format, the tracks 0 and 1 contain metadata, and that is generally things like the track listing, things like that. A file occupies a track. Because we don't have those sectors, that the file can't be split up and put onto different sectors, so it means that one file equals one track. No matter how large or small the information is, one file is one track. Now files can occupy more than one track, but they must be sequential. That means if you start a file on track 20 and it goes over the capacity of that track, then the next track has to be track 21. There is two types of data that get written to the disk. These are computer data, and that is data that's used by the actual computer cards. So this is generally things like metadata, things like file listings, image names, sizes of bitmaps, that kind of thing. The other data that's stored on the disk is called video data. Now this is actual just raw bitmaps of images. These are sort of full screen images, cutouts, fonts and brushes, and also things like stencils, that kind of thing. Now the video data is 8-bit digital samples of YUV video with chroma subsampling at 422. This format is the same that is used on the later Quantel machines like the V-Series, Paintbox, HAL, Editbox, that kind of thing. So just to make a point that there is a differentiation between different types of data. The video data contains nothing that is readable by the computer, and likewise the computer data is not used at all by the actual main hardware painting side. The computer data is literally just used by the computer, and the video data is only used by the main painting hardware. So let's have a look at a bit more of the specific details on how a track is actually written to the disk. So on the DPB floppy, we have a total of 19,200 bytes per track, and that's split over the two sides. So we have 9,600 bytes on each side of the floppy disk. The host to drive data is a single serial line which is clocked at 500 kilohertz. The data that is transferred between the DPB and the drive is clear 8-bit data. It's not MFM encoded by this point. The MFM encoding is done by the SMD to floppy interface board, which is located inside the floppy drive. So if we actually have a look at how a track might be laid out, this is a flat representation of the entire track. So this would do the start, and that would be the end, and then that would wrap round as the disk rotates. At the falling edge of the index pulse, there will be a period of zeros written. Now this is written in clear data, so by the time this is actually MFM encoded, those zeros become 10, 10, 10, 10. So it generates a pattern to lead into the track, and then the next thing that happens is we have a sync byte. This is just one single byte of data, and it's 0x53. So this generates a particular bit pattern which is picked up by the disk buffer card. Once that happens, it then starts transferring the 9,600 bytes of data which is on the remainder of the track. Now, as I said before, that either goes to the disk buffer, the RAM that's on the disk buffer card, or it gets injected directly into the system bus and into one of the stores in the DPB. And because we have two sides, there is a point where the machine switches over and reads the second side to get the full track of data that is available. Now, at the moment, we're not quite sure what mechanism causes the DPB to switch sides. We're pretty certain it's not software. We think there might be a hardware thing going on somewhere, possibly in the disk sequencer. When it knows it's working with floppy drives, I think it does a switch over at some point, but how it determines that, I'm not entirely sure. So the data plays out along the track, and at the end of the data we have another sync byte, 0x53. I'm not sure if this is actually really used in the software. I can't really understand how it would be, but it is definitely there. I've actually looked at all these on a logic analyzer and grabbed entire bit streams that come off the disk. Interesting little point is the index pulse. It is actually quite large considering the size of the actual overall track, so you do often see data overflowing into the high portion of the index pulse, but of course it's just the falling edge that we're interested in, so it's able to sort of move into that area. So next to look at is the DPB hard disk. Very, very similar to the floppy disk track. We have 19,200 bytes per cylinder. The host to drive data is again the serial data with a clock, but this time it runs at 8 megahertz. Again, the data is clear 8-bit data. It's not MF encoded by the DPB because the actual drive itself does the MFM coding. And you can see here the pattern is pretty much identical to a floppy disk one. We have an index pulse, we've got a lead in, sync byte, the data, sync byte, and then the end of the track. But of course, because we can now fit the full buffer of 19,200 bytes into an entire track, we have no changeover point onto another side, which doesn't really mean anything in terms of a hard disk anyway. So now we've looked at all that, let's take a look at what the emulator might be looking like. Right, so after that rather long intro into the disk formats for the DPB, let's go back to the cards. So we've got the disk buffer and the disk sequencer, and we've got the SMD interface. So the thoughts have been is to actually replace this card here, which is the SMD interface board. This has all of the actual signals on that we need because they go out to the drive. We don't want to mess around with SMD signaling because it's all ECL and that's just horrible to work with. All we want to do is get the actual data that's coming off these cards, which conveniently comes onto this one. So what we're going to try and do is replace this card with the emulator. So this PCB has been very, very kindly made by PCB Wafer. I want to thank them massively for making this for us and supporting what we do here. So this is dimensionally the same as the SMD emulator, so this will plug in place of that and then pretend to be the hard disks that would normally be attached. So yeah, it's an absolutely beautiful PCB designed by Electron Ash. So we've got a nice edge connector down the side. This has all been gold plated and beveled, routed out by PCB Way. So what is actually going on onto this card? Well, Ash recommended the DE10 because more than likely he's going to be doing most of the coding for this, and he's very, very familiar with the DE10 Nano. So the original plan was to have this mounted on here. We'd have some buffer chips on here just to buffer the between the old cards and the DE10 because there is actually an issue with the 3.3 volt signaling. Obviously these older cards being TTL, that's all 5 volts. So we needed a buffer in there anyway, and it's good practice to have some anyway. That would plug onto there, and there'd be a ribbon cable which would just jump over down onto here, and then that would make contact with all of the edge connector. In addition to this, we've also added a load of LEDs. These are just status indicators, it might help debugging, so we thought, why not? And we have another port here, which is literally just breaking out the signals, so I can plug in a logic analyzer if I need to. Now, one of the little issues that we came across, which is partly my fault, these cards plug in the back of the DPB round just over here. So they plug in this way in, as you're looking at it, with the side of the case right up against it here. Now, we've designed this so the components are on the same side, but we kind of didn't really account for the thickness of the D10. So there's going to be a little bit of creative stuff going on here. What we're going to do is actually mount this on the other side, so this will still plug in that way. The D10 will go on there like it was before, but just on the other side, and we'll come down to a pin header on here. Now, because this has been swapped over, everything's mirrored, but that means we can't just have a ribbon cable now, because if we twisted it round, you'd also swap top to bottom. So I think what we're probably going to do is I'm going to make up some cables like this, so I can separate the two rows of the connection pins, just so we can connect it onto this side easily. So the way that we're hoping this is going to work is this will use the signaling that comes out of the disk sequencer card to select a track of data that's located on probably on the micro SD card that's already in here. It will probably use the same sync byte that the disk sequencer is actually looking for, because we can use that to pick out what is actual data as the DPB is writing to the disk, and then write that, just the data, into an array on the SD card. And when it comes to playing that data back out, the D10 itself can actually generate the pause and then the sync byte, and then it'll pull the data out of the SD card and then output it all to the DPB, hopefully. So what I'm going to need to do now is make up a new one of these. I did buy this potentially as a solution, but the cable's just way too long. It literally just needs to go from here to there. So I think I'll probably just make my own. I've actually gone away and bought myself a DuPont cable making kit, so I can just make my own. I also need to go through and solder up all the components on this to get them all done. So these are actually arrived here, so we've got those to do. So these are mostly just passive stuff. Right, that pretty much concludes everything that we need to talk about. I'm going to go away now, get this made, get the D10 on it, get it programmed with the software which Ash is currently working on. So before I go, I just want to thank everybody who's been involved with this. Thank you so much for all your help and support. And of course, let's not forget all the viewers and the people that like and comment. Thank you very, very much. Right, I'm going to go away now, and I'll see you in part 7. Bye for now.